Yeah, so Delia is the CEO of Earth Building Association New Zealand, so we're very privileged to have her today. And Mingtong's from Canterbury University, also working on the research together with Delia. So I'll hand over to you. So
thanks.
Finish up before we get to lunch.
Yeah, and thank you for inviting us to present at this conference. I really respect the work of the Passive House Institute, and I sort of look forward to working with you a bit more as an organisation, because I think we can learn a lot from each other. But I'll give you a bit of an overview of EBANZ initially. So really, we're talking about natural materials and the potential of natural materials to really improve building performance and embodied carbon, as well as occupant health and low toxicity. So EBANZ, the Earth Building Association of New Zealand, is a network group consisting of architects, engineers, builders, academics, and people generally interested in using natural materials. And these are materials and techniques that have been used across the globe, across all cultures for thousands of years. And the techniques can be sort of categorised as heavy earthen materials, so adobe, cob, rammed earth, right through to lighter earth, hempcrete and straw bale. Here's some really cool international contemporary examples at the bottom. The key ingredients of all of these techniques are these three things: a fibre, so that might be straw, hemp chaff, flax, binder being clay predominantly, also some lime, and aggregates like sand and gravel. So three natural materials in different ratios, creating a variety of different techniques. So the carbon footprint of this is relatively low, and the toxicity of this is relatively low, especially in terms of human health and waste material. So you can see here is some modelling that was done by Andrew Alcorn, who is one of our founding members, and this is part of Brands Construct. But you can see that negative figure means that this is sequestered carbon. So this is stuff that's been absorbed by the fibre and then stored, and so it can be stored within the building. Now, this is a full life cycle analysis, so this is including, production, combine harvesters, tractors, all of those kind of things. You can see also a lovely picture of straw being burnt. When we went up to Geraldine for the International Straw Building Conference in 2017, there was enough straw being built to build about 20,000 houses. And obviously all that carbon is being released. We're talking about trying to lock that carbon into buildings. And why not use a resource that's already there, having grown food or grain or something that we can, actually live off as well. So these materials, so we go from light straw bale, which has got an increased R value, decreased thermal mass, right the way through the gamut. So all of these, what happens is the ratio of fibre, the ratio of clay shifts. So when we get to the end, rammed earth pressed brick, that is probably no fibre, a lot of clay, a little bit of sand, very high compression. So a lot of thermal mass, but poor performing from a thermal from an R value perspective. EBANZ in the late 1990s developed the first legislative standards in earthen building in the world, so gained a lot of respect at that time. The standards have recently been updated to reflect sort of current best practice, but they are very much focused on earthen materials, and they were really focused on empowering people to be able to source local materials, test them and use them to make buildings for themselves. So kind of providing a sort of a standard for vernacular architecture, which is actually a really important and empowering thing. However, it probably has given us a little bit less ability to kind of interact with the mainstream, where we're talking about large commercial applications rather than things that are done by people in their own backyard. So what we're trying to do now is focus a little bit on how we can sort of get these materials more into mainstream construction, maybe with more hybrid things. But we really believe that these ancient techniques offer real solutions to the problems we're experiencing today. So we're really focusing on education, we've got a lot of collaborations underway, and also performance testing. So one of the components of this discussion is talking about the performance testing we're doing with Mingtong and her team at Canterbury. A couple of case studies for you of some existing passive houses within New Zealand that are using straw bale. Haven't got any carbon footprint rates for this, I don't believe, have we, Jess? But that would be something that would be really good to do. But you can see some great results. Another one that's recently completed. I believe Rachel is here today as well. Yeah. And so, yeah, you can see, look at the air leakage rates here. And all of this, obviously there's tapes around windows and tellos at ceilings, but this is the clay plasters that are doing this work, including, I think, a casein paint in the case of Rachel's, which is also a natural paint. We'll talk a little bit more about the importance of that construction envelope in a moment. And there are some really innovative things happening as well. So we've got straw panels. You see some good examples of this outside too. So where one of the key issues with the uptake of natural buildings is, although the techniques are simple, there's a high labour content. And if things are done incorrectly, there's failures. So that's, we need to manage that. But trying to reduce the labour content with some prefab consideration, but also trying to balance that with, we've got this great carbon solution by not having a lot of fabrication, and how do we get that balance? So here is a bit of a comparison that Elron did with Ben on these particular panels, just to show that even with the manufacturing component, still stores 4 times as much carbon than is emitted during production, and emits only half as much upfront carbon as a comparable timber frame wall, even though actually the performance is better. And the other thing is that carbon is being stored in a growing season, not in 20 to 40 years of tree growth, and it's growing a food crop that we can eat and use. Another innovation which is really exciting is hempcrete and the binders used for hempcrete. Traditionally, our organisation has been a little bit wary of hempcrete because it's got crete in it. There's a lot of lime there. But Doug Sturrock and GeoBind has developed a binder which has no slaked lime in it. It's using magnesium oxide and kaolin clay. A couple of other commercially secret ingredients in there I'm not sure of, but still percentage-wise doing pretty well. So he hasn't done any carbon footprint data as yet, but it's definitely lower than slaked lime. And there's also with magnesium oxide, we know that there is some carbon storage going on during processing, and it's certainly very low toxicity. You don't slaked lime, you're wearing a lot of kit. It's hurting your eyes, your lungs. That's not the case with this product. The other really interesting thing about this product is performance. So he's had testing done with Callaghan Innovation. So these are traditional binders, predominantly lime. His compressive strength, phenomenally better. Second graph, that's compressive strength with a lot less binder as well. So it's still achieving better compressive strength with less low carbon material, less toxic material, and less binder material too. So there's real potential for this, and it'd be interesting to see the potential for that even within more cretes, within a concrete as well. So moving on a little bit more to that kind of performance and moisture. So we're talking a lot about how we regulate things within buildings, and within Passive House specifically, trying to kind of create this optimum envelope where, we're kind of allowing regulation to happen in a very controlled environment. I believe natural materials have got a lot to play within that, because they're already doing a lot of complex regulatory work because of the very nature of them. So clay has a high hygroscopic behaviour. You can see that's compared to gypsum. So, almost 4 times as much in terms of what it can absorb and release. So as soon as it maintains a very even moisture humidity content within a space, which is optimal for human health, just by naturally how it performs. But it is really critical that the makeup of that wall works so that vapour can still escape. So, obviously on the outside of the building, we want a non-eroding, robust building envelope. So eaves are pretty critical, which does, make things a bit difficult with modern designs, but that's something we need to work on to make roofs more beautiful again. But also lime plaster, which effectively gives you a very sort of 3 to 5 mil of sort of limestone on the outside of your building, but it's still vapor permeable. Natural paints as well that are vapor permeable. Anytime we put a cement plaster on, moisture goes through, gets trapped, even affects adobe cob. It's not just straw. So a lot of historic cottages that were restored in the 70s with cement plaster on the outside, concrete slabs inside, we have to go in and strip that cement away, strip the concrete away to stop the cob from actually deteriorating. So the fact that they were trying to protect has caused damage. Thermal mass, of course, if we're putting lots of clay into buildings, which we are when we're using rammed earth or clay plasters over straw or earthen floors, we are allowing ourselves to get the benefits of passive heating and cooling. And obviously within Passive House, that's again because of that controlled environment is a different, that's not necessarily something we're wanting to achieve, but there is certainly potential. And interestingly, as Mingtong will talk about some of her findings, actually natural materials for thermal mass definitely seem to have a good correlation with Passive House designs. This is another area where we can be looking at more, how do we get into the mainstream and incorporate materials within conventional or passive house structures. So, you know, not everyone's going to want a full straw bale house or a full round earth house. We can do an earthen floor. So commonly that is just a 20 to 40 mil topping over a concrete slab. You know, some clients who are really into removing concrete as much as possible are doing sort of 150 mil compacted earth floor over a gravel, a compacted gravel. I've found in practice that often we end up with ring beams and floor beams that, you know, increase the concrete volume. So, you know, potentially a bit counterproductive. But, you know, certainly floor toppings work really well. There's less requirement for heating of the floor as well, because earth is actually a really nice substance to stand on, as opposed to concrete. And you're getting actually a softer thermal mass, as we'll see shortly. The other thing is a clay plaster doesn't have to be over a straw bale, can be over a substrate, could be over gypsum or fibre cement board or even recycled carpet, anything that it can key onto that can give you some thermal mass and hygroscopic performance on timber framing. There is also some development within members of the group into creating a sort of plaster board, which is using clay or flax or clay and straw. That's a pre-finished board you can literally just fix to a wall. And the adobe brick veneer is another option. Really gives a very beautiful effect, but it's still a pretty grunty brick. But you know, that can then be put on with veneer ties inside a building if you really want some decent solid mass. But of course, you could also do a round earth wall or a hempcrete wall if you wanted more of that strata effect. It's just a lot bigger and more structural requirement. Right, so this leads us on to Mingtong, who's doing some research with Canterbury University.
Yeah, my name is Mingtong, and like during the thermal mass simulation process, we considered New Zealand's different climate zone, like as indicated by the NZBC H1 climate zone map. And we selected Auckland from climate zone 1, Wellington from climate zone 3, and Christchurch from climate zone 5. And modeling allowed for elevation relative to the sea level variation to simulate similar climate situation. For the carbon emission simulation in different climate zones, we selected an experiment house in a commercial building on the 3rd floor. The map on the left, the map on the left shows the relationship between electricity consumption usage and the carbon emissions. And where the color gradient from the light to dark means represent the intensity of the carbon emissions. Also due to the, you can see from the Wellington one, that was more dark because of the different weather, maybe Wellington is more windy and the diurnal temperature is more big. So the HVAC system tends to have a higher operational energy consumption. And the right of the bar chart, it shows that across all of the regions, building utilizing nighttime natural ventilation with the thermal mass, yes, yeah, which can generally consume less energy compared to those only use the HVAC one. And now that one is an example from Auckland, yes, and it can shows more clearly demonstrate that use the thermal mass can effectively reduce the operational energy system, and also furthermore, selecting energy suppliers with a higher share of renewable energy can also significantly lower the carbon emissions. Also, we focus on the building envelope materials. So we conducted simulations for different weight buildings and earthen envelope buildings. Also, for the medium weight buildings, we select the brick as the building envelope, while the earthen one, heavy one is the concrete. And for the earthen envelope, we choose the round earth walls. The simulation case, we use the window to wall ratio was 0.223, and also for the building volume is 305.72. The thermal mass material is always on the floor, and there is no any ventilation.
We decided to model it without ventilation to more closely reflect what might happen in a passive house situation, because within the modelling that Mingtong team is using, there's only kind of full natural ventilation or quite high volume air ventilation with a HVAC system. So we were just trying to see what would happen if there is no airflow, what that might do for thermal mass, because obviously it usually relies on, you know, airflow to allow the cooling to occur.
Yeah. And also that one is also we use Auckland as an example. We select the summer period from November 1st to April 30th. And For the medium weight building, we compare the indoor temperature variation over a 48 hours period from 28th to 29th from January. The yellow area on the graph represents the temperature difference between the two types of envelope systems. It is evident that using earthen wall that as an envelope really helped to maintain indoor temperature within a more stable regions. Also, we have the similar results from the heavy building. You can look from the figure. The temperature range for discharge cooling for the clay material, which means the earthen envelope building, is less than other materials and is really reflective of temperature range permitted with the passive house designs. And now Delia is the expert of the materials. We will choose through for the sensitivity analysis.
Yeah, well, I didn't do the sensitivity analysis. That's your expertise. So all of this data that Mingtong's showing you has been done with simulation, but there's also been some testing physically done within a laboratory. And so the sensitivity modelling has come from an evaluation of both of those elements. And you can see that clay sheet is doing quite a lot of work in a narrow thickness, but it's also doing it within kind of a temperature range that's kind of optimal for sort of healthy living as well. We're not having to get really cold or really hot to allow that clay to do the work in thermal mass heating and cooling. So there is real potential for clay within passive house buildings, I believe, and any building to have a real impact. In terms of just being able to do some regulation, I think overheating, especially if we've got any solar gain, there's going to be some solar gain in buildings. We need that. We're regulating it, but if you've got a concrete floor that's getting that, it's going to have more impact for overheating if you haven't got the ventilation to cool that off, especially if that slab's also heated. The risk of actually overheating that space and not being able to cool it down. So yeah, the thermal mass definitely reduces operational energy emissions, and by using earthen materials, we've got potential for that to also reduce embodied energy. And I really think that we would like to do more research into looking at how thermal mass performs specifically within PHPP, just to see, what could be beneficial. Thermal mass isn't really accounted for in a particularly detailed way within PHPP at the moment. So I think that's something that would be important, certainly for any other types of energy modelling. It is important. And the fact that we can use less of the material to get a good result is also important. So yeah, further simulation modelling, verified by physical testing for different constructions would be great. And I think, it'd be great to link you guys up together to have a bit of discussion, because Mingtong is not a passive house PHPP expert. So I think we could really further that research a bit there. And then also in terms of the external envelope, earthen walls are, in terms of having very little insulating quality, are sort of things that are not going to be valid to use really as we move forward. So it'd be interesting to see how thermal mass can work with thermal comfort, and if that does give potential for earthen walls and exterior envelope to be used a bit more. And then the real outcome, which is the most exciting thing from Mingtong's research, is the thermal mass plugin, which is being developed to be used to tie in with other energy modelling software. So there is something that's a lot easier to take account for, and assess. And so what next for natural material? Well, we want to continue our work with various universities and entities and anyone who's interested. And that's also going to be looking at moisture management. So we know from occupant experience that these buildings are really nice to live in, but we really do need verified data to justify to people and get people on side that this does work. We're also working on industry upskilling for designers and trades and for councils, because, a lot of people are wary of these materials or don't understand or don't believe that they can work. More carbon footprinting, because yes, whilst we need the action, which we really do, sometimes you've got to have the paperwork to encourage people to want to do what you're doing. So yeah, we'd love to have some further work in this. And I also believe there is potential to increase those tie-ins with agriculture. It's an existing industry where also other things like aquaculture. Somebody was talking to me the other day about kinocrete or using mussel shells, waste products from other industries, which are natural biomass or naturally derived materials that we could be using to create materials. So some sort of product accelerator that's supporting innovation in these things, that's taking a problem from another industry and locking that carbon into our buildings. I think there's real potential here. So yeah, hopefully that's given you a bit of an overview of what we do, and yeah, feel free to come and talk to us and ask us questions in more detail.
Thank you. That was a great presentation. Really, really exciting.